dwarf was detected in the Phoenix constellation. It was later to be dubbed WASP 96. The year 2013. The Super WASP orbital telescope detected an extremely rarefied gas giant in the immediate vicinity of the star. A preliminary spectral analysis of its atmosphere revealed that it was remarkably transparent and practically devoid of any water vapor. The year 2022. Analysis of the object's atmosphere was conducted again, this time with the help of the new generation orbital telescope James Webb, which offered an unprecedented accuracy. Scientists were taken aback. If the new data were to be believed, the exoplanet was supposed to be shrouded in thick layers of clouds, which was the exact opposite of what the previous observations had revealed. Thus, the data from the James Webb was in conflict with the earlier estimates, and the degree of our understanding of the universe was questioned yet again. So, what is this amazing telescope like? And what has it seen in the depths of space so far? Let's take a closer look at it. Back in 1996, its development and modernization took as long as 25 years, after which the spacecraft left our planet and set out on its journey through space. It took James Webb a month to reach its destination point, located 1.5 million kilometers from our planet. Because the telescope is equipped with high-precision infrared sensors, it can see the dimmest and most distant space objects hidden in the depths of the universe. However, this unmatched sensitivity also has a downside. The intense radiation from the Earth, the Moon and the Sun interferes with the faint signals of distant stars and exoplanets. Therefore, in order to counteract this effect, the super-sensitive instruments were covered with a multi-layer heat-reflecting screen. The observatory itself had to be moved away from large celestial bodies and be located near the so-called second Lagrange point in the shadow of our planet. Still, the obtained results were absolutely worth all the effort, because James Webb helped us make quite a number of amazing discoveries pretty much from the very first days of its operation. With some of them quite expected, others, on the other hand, prompted additional questions. One of the studies with a paradoxical outcome was the spectral analysis of WASP 96b, a glowing exoplanet of extremely low density. It is located 0.045 astronomical units from its parent star and completes a full orbit around it in just 3.5 days. According to calculations, the mass of the celestial body is half the mass of Jupiter, and its diameter is 20% more than that of Jupiter. Because of the extreme proximity to the star, the temperature of the object's outer layers is quite high and reaches 1285 Kelvin, or just over 1000 degrees Celsius. Exoplanets of this type fall in the category of hot Jupiters and are distinguished by large losses of atmosphere due to stellar wind. Earlier measurements showed very clear lines of sodium in the atmosphere of WASP 96b, which was interpreted by the researchers as a sign of an unusually clean and cloudless atmosphere. The fact is that according to the available models of the structure of gas giants, this element can exist only in the planet's interior. As we can see traces of it, it means that the upper regions of the celestial body's atmosphere practically do not absorb light. It was assumed that thanks to this, the ultra-sensitive detectors of James Webb could look into the deepest layers of the exoplanet. However, the information obtained by the telescope turned out to be radically different. The outer layers of the gas giant contain great amounts of water vapor. It condenses in the upper atmosphere and can form a large haze or thick clouds, reflecting some of the light shed on it. Because of this, the temperature of the lower layers of the object may differ significantly from the calculated values. Perhaps the accuracy of the earlier study was insufficient, or else some of the data was misinterpreted. It is also possible that we do not yet know of a certain factor that would allow us to combine the results to form a single correct picture. WASP 96b remains a mystery, which means it still needs to be studied in more detail. Of course, James Webb's discoveries do not end there. For example, 69 light-years away, there is an unusual system consisting of 3 brown dwarfs at once. These cosmic bodies are too big to be planets and at the same time too small to launch a stable thermonuclear reaction in their interior. Brown dwarfs are usually difficult to detect, as the radiation of their surface is extremely low. But James Webb sees the universe primarily in infrared, which makes it easy to distinguish objects that are virtually invisible in the optical range. The 2 largest components of the system are very similar in their characteristics and are located quite close to each other. The distance between them is about 2 astronomical units, and their total mass is slightly more than 100 times that of Jupiter. The temperature of both objects is relatively high, reaching 2600 Kelvin or slightly over 2300 degrees Celsius. The third component of the system is at a much greater distance, about 100 astronomical units from the center. Its mass is between 14 and 23 Jupiter masses, and its radius is 20% more than that of Jupiter. Also, this brown dwarf is about twice as cold as its more massive companions. Observations reveal that the temperature of its outer layers is 1240 Kelvin or slightly below 1000 degrees Celsius. Nevertheless, the celestial body is considerably warmer than the gas giants in our system, especially given the absence of a star that would give it heat. It was surprising to find that the outer layers of this brown dwarf contain not only the usual components such as water, methane or carbon dioxide, but also minute particles of various silicon compounds. The simplest of these is quartz, but more complex substances have also been detected. These are thought to be concentrated in the atmosphere of the celestial body in the form of vast clouds. The existence of such clusters had previously been predicted from theoretical considerations, because silicon, being a product of stellar thermonuclear reactions, is quite widespread in the universe. Still, until recently, observations have not been able to confirm this hypothesis. It is thought that about 140 million years ago, there was a single gas dust cloud in the system's place, which later split into 3 independent clumps. This event may have been caused by the gravitational influence of a massive celestial body that passed close to the protostellar nebula. Remarkably, if the separation had not occurred, the total mass of the formed object would have been enough to start a self-sustaining thermonuclear reaction. In this case, instead of 3 brown dwarfs, we might have been observing a single tiny star. Incidentally, the James Webb equipment is capable of observing not only single objects tucked away in the depths of space, but tremendous space structures as well, that stretch for hundreds of light-years. One of them is the Carina Nebula, which is one of the largest stellar nurseries in our galaxy. This bright and vast cluster is located about 8,500 light-years from the Earth and has a mass of up to 900,000 suns. It contains not only giant clouds of interstellar gas and dust, but also thousands of stars, from the smallest ones to the most gigantic. This is where 2 of the Milky Way's brightest objects are located, Eta Carinae and WR25. The luminosity of each is several million times greater than that of the Sun. Unique objects like that certainly attract astronomers' attention. Besides, James Webb's infrared cameras are able to pick out great numbers of stars in the dusty haze, which were previously unknown to us. The point is that it is in this area in space that hundreds of young stars are constantly getting born. According to modern concepts, new stars are formed by gravitational forces that compress and heat up clouds of cosmic dust. During its evolutionary process, a protostar goes through several stages until finally a thermonuclear reaction kicks in its interior. This theory has been confirmed by multiple observations, but many details of this long and complex process currently remain understudied. The formation of a new star sometimes takes millions of years, but astronomers don't need that long to observe it. Thanks to James Webb's infrared sensors, thousands of protostars and young stars at various stages of evolution have been detected in the Carina Nebula. It is important to note that all these objects formed within the same gas cloud, which means that they are very similar in terms of composition and age. By observing them, researchers can fully trace the process of star formation and better understand what forces are involved. Some phases of this process, predicted only in theory, take hours or days, and with James Webb, the chance of capturing them is greatly enhanced. For all we know, we may soon be able to admire a photo of a young star flaring up thousands of light years from the Sun. Meanwhile, an 18-section mirror 6.5 meters in diameter and an onboard array of high-accuracy instruments allow James Webb to capture light from objects much further away, at the very edge of the visible universe. They are more than 13 billion years old, giving us a glimpse of the earliest times immediately after the hypothetical Big Bang. However, even James Webb would not have been able to see their luminescence but for one unique coincidence. The phenomenon of gravitational lensing has long been known to scientists. This physical phenomenon helps us to better see into the depths of the universe. And this is how it works. A powerful gravity generated by a massive body focuses and amplifies the light from a source behind it. Such an effect can be produced only on condition that a great many factors happily combine, so it is not surprising that it is one of the rarest phenomena in the universe. It is all the more surprising that while observing the galaxy cluster SMACS 0723, located about 4 billion light-years from the Earth, James Webb captured light of a space object passing through gravitational lenses as many as 3 times. In total, the radiation was amplified about 20 times, without which astronomers would hardly have been able to distinguish it from background noise. The object is thought to be a distant and very old galaxy, whose age is estimated to be 13 billion years. About 10 other star clusters have also been detected, which are thought to have originated between 200 and 700 million years after the genesis of the universe. According to some observations, they have a complex structure which takes tens of millions of years to form. This discovery will allow scientists to develop the existing ideas about the early stages of the universe's evolution and may even prompt to question its age. Unfortunately, we still know very little about such remote times, and James Webb will surely help us learn more about them. The state-of-the-art telescope has pushed the boundaries of our cognition to the very edge of the universe. There are likely to be dozens of discoveries hidden in its images right now, waiting to be soon interpreted. Meanwhile, the James Webb mission has only just begun, and there are years of operation up ahead. We will be following its progress and hope for